Welcome to massive open online course on basic principles and calculations in chemical engineering. So, we are discussing about fundamentals of material balance under module 3. Under this module today we will describe about the material balances on chemical reaction process, especially for combustion reactions. And in the previous lecture we have discussed and also solved the problems of material balances on reactive processes, especially with selectivity, yield, efficiency and extent of reaction. Now, we will discuss more about that material balance of chemical processes where reaction will be involved. But in this case we will describe something about the processes which will be involving chemical reactions as well as bypass, recycle and purge with makeup also. And then next part of this lecture we will describe about the combustion processes and also try to solve some problems about that combustion reactions and how to do that material balance with those combustion reactions. So, let us first discuss about the that material balances with reactions based on that recycle, bypass, makeup and purge. So, before going to that we of course recall that general material balance equation which is basically that accumulation is equal to input minus output plus generation minus consumption. And since this material balance involving with that chemical reactions, here we have to consider that generation and consumption terms. But if this reaction processes is at steady state condition, then we can say that accumulation will be equal to 0. So, let us have this problem of that chemical engineering processes which will involve these chemical reactions here, like if we produce benzene from the toluene, then how this process will be executed with different process units. Let us have this process unit here. There are several process unit will be utilized here for this benzene production from the toluene. Here some mixer, reactor, separator, even the divider, and then you can say that mixer will be used after makeup there. Now, what is that actually that reaction process which is actually going on during that benzene production process. In this case toluene will reacts with hydrogen to form benzene, but a side reaction will also occur in which a byproduct like diphenyl as denoted by D here is formed as per reactions. Here the reaction is given like that this in this reactions here toluene is reacting with hydrogen and will give you that benzene and methane. And this products of this that benzene production along with that there will be some byproducts will be produced. In that case this toluene again will be reacting and then the byproduct will be coming out as a diphenyl along with that methane. Now, in this case hydrogen is added to the gas recycle stream to make the ratio of hydrogen to methane that is 1:1 before the gas enters the mixer. Now, this ratio of hydrogen to toluene that enters the reactor at at a certain amount, let it be G here as per problem given, and that will be equal to 4 times of hydrogen to 1 toluene. Now, this reaction conversion of the toluene to benzene will be single pass through the reactor that is 70%. We have described the definition of overall conversion of the reactant and also single pass conversion of the reaction that is that for the particular process unit is given in the previous lecture. So, as per that we can say that the conversion of toluene to benzene in a single pass through the reactor will be 70%, and the conversion of toluene to the byproduct that is diphenyl is 6% on the same pass. In this case you can assume that 100 moles of toluene in the stream G. So, what should be the flow chart? First you have to draw, and also in the flow chart you have to write the component material balance for each component for the unit reactor plus separator, and write the component material balance for each component for the unit mixer, and then calculate the moles of Rg, Rl, M and P per hour. So, here in this slides this flow chart of the process is given here. So, here see that mixer, in the mixer the feed is coming that is 100% toluene, that is pure toluene is coming to the mixer, and in this mixer some gas will be entering as a gas recycle along with its makeup, and also liquid recycle also will be entering here in the mixer, and after that from this mixer gross amount of feed as a G will be coming into the reactor, and after that reaction you will see that several products will be coming out like that as per reactions whatever components will be coming out along with the byproducts will be there. After that those product streams with different components with product and byproducts, it will be sent to the separator, and after that some processing of separation you will see that it will be divided into several components. Here that product will be coming as 100% pure benzene as a B, and where byproduct will be taken from that separator as a D. Here that will also 100% diphenyl will be taken as separate stream, and then some amount of gas like whatever gas is produced there, that is methane gas, along with unreacted gas like hydrogen gas that will be recycle back to the mixer, but if there is some that unreacted materials are there or inert materials will be there, that will be purged as a P here from this outlet, and the gas recycle as amount Rg it will be going to that mixer along with some that some amount of hydrogen gas as a makeup to be given, because some that hydrogen gas may be lost because of some leakage or some other dispute of that instrument there. And after that also whatever liquid product as that will be after separation it will be taken out as a byproduct, and then that some liquid recycle, that is toluene, that is unreacted toluene as a liquid, it will be recycled to the mixer again, and after that from that mixer the that stream as a gross feed denoted by G, it will be again sent back to the reactor. So, in this way this whole process is going on. So, we can that specify that stream amount, what will be the components are there, and we have given here in the slides in the picture here. See this is total flow chart of the process. Now, for this particular process you have to do the material balance based on that general material balance equation. Now, let us do that material balance one by one. Here one important things that you have to remember, here not only single unit, multiple units will be considered for the system at a time, even sometimes two that units, process units will be considered as one single system, even only one single system or single process unit will be considered as one single system there. So, based on which sometimes for convenience of your calculation you have to consider that more than one process unit will be as a process system there. Now, let us solve this problem one way here, like if we consider that 100 moles of toluene in stream G after mixer here, then if we consider the system as reactor and separator and considering both the units here as a system, and then if we do the material balance for each component here, then what we can write. Now, as per material balance equation, we know that if there is a steady state operation, then we can simply write there in minus out plus generation minus consumption. So, here since reaction is going on, we can consider that generation and consumption there. But some reactions maybe there will be no generation, but consumption will be there. Some other that there may be generation, there will be no consumption, like this. So, let us have this here. If we consider first the toluene, then what will happen, that what will be the input of that toluene. This is given that toluene is coming as 100 moles there as a G. So, we can write here this that toluene as 100 here in, and then out, what will be the output of that toluene. Since here from this system this toluene is coming out as a recycle here, then what happened, this recycle amount is considered as RL here. Since it is not known to you, we are considering that amount will be RL. So, simply we are keeping that symbol as RL here, that amount. So, 100 minus RL. Now, then plus generation. Now, what will be the amount of generation of toluene? Since here there is no formation or generation of toluene, this is only supplied, but there is no formation of or generation of toluene based on the reactions. So, we can write simply generation of toluene will be equals to 0, and consumption. Now, since there is a reaction, based on that reaction equation, toluene is reacting that with what is that hydrogen, and it will give you that benzene and methane. So, we can write here that consumption of that toluene will be what? Since this toluene is going to that reactor, so one pass conversion is given 70%. So, here 100 into 0.7, this much of amount of consumption of toluene will be there. But along with that, there will be other consumption there, that here it is said as per your problem that here some conversion of toluene will give you that byproduct diphenyl which will be 6% on the same pass. So, you have to consider that 6% of conversion of toluene there in the consumption term. So, it will be coming as here 100 into 0.7 plus again we 100 into that is 0.06. So, this total consumption of the toluene will be like this 100 into 0.70 plus 0.06. So, this is the equation we can write for the component toluene. Similarly, we can write the balance of the component for hydrogen, like what should be the amount of hydrogen is coming into the system, that is for that combination of reactor and separator. We can simply write here that since G amount is 100, but there that it is said in your problem that hydrogen is added to the gas recycle stream to that make the ratio of hydrogen to methane will be 1:1 before the gas enters the mixer, and also it is also told that the ratio of hydrogen to toluene entering the reactor at G will be 4 times of hydrogen to 1 mole of toluene. So, in that case we can simply write that hydrogen amount will be 4 times of that toluene amount. The toluene amount is 100, whereas this hydrogen then will be equals to what is that, this 4 times of 100, that will be 100 into 4 like this here. So, it will be your in, and what will be the out? That outlet amount of hydrogen, it is not known to you. we can simply assume that this amount of mole of hydrogen at this outlet will be equals to what? This is NH2 here, and also we can say that here the separation in the separator, you will see that after separator this hydrogen will be coming out as this amount. And then what is the generation terms of that hydrogen? Since you know that there is no hydrogen is generated during that reaction, we can simply say that generation term will be equals to 0, whereas consumption of hydrogen will be there since there is a reaction with that hydrogen. So, hydrogen consumption will be equal to 100 into 0.70 into 0.06 into 1 by 2. Why that 0.06 into 1 by 2? Because 1 mole of toluene is required that half moles of hydrogen in the second reaction production of byproduct. So, that is why we can say that here 100 into 0.70 and plus 100 into 0.06 into half mole of hydrogen is required for, and it will be considered as a consumption there, and that will be equals to total here this as per this equation it will be equal to 0. So, all these equations it is coming 0 because that accumulation term is 0. Similarly, you can do the methane balance, it will be in the 100 into 4, that is in here, and methane that is coming out from that separator here it is not known to you. Let us see that this will be equal to N methane there, and here what is that this generation terms of the methane, because this methane is produced after reaction. So, that is why generation of this methane will be considered there. So, what is the amount of generation of methane will be equal to per 100 mole what should be that amount, because conversion is 70% and also there 6% of byproduct is produced based on that reaction with hydrogen gas. So, 1 mole of hydrogen is required to give you that it is 6% of that diphenyl. So, accordingly you can say that total how many moles of that methane is required for the generation of its methane gas. And also consumption, in this case methane is not consumed because there is no participation of the methane for the reaction, only it is coming out as a product. Now, solving these 3 equations of this material balance of components, we can have this RL will be equal to 24 moles and hydrogen moles that is coming out from the separator as 327 moles, and methane gas which is coming out from the separator that will be equal to 476 moles. Now, after that there will be other variables to be estimated based on the material balance, like you do not know what will be the amount of feed in the mixer. So, based on the consideration of the system of mixer unit, we can also do the same component balances, but there will be no chemical reactions. So, accordingly we can say that there only the material balance equation will be equal to N will be equals to in is equal to out. So, based on that toluene will be equal to what toluene balance will give you that what will be the amount of toluene is coming into the mixer, that will be F into 1. Why 1? Because here 100% toluene is there, there is no other component in this mixer. So, that is why you can write there this fraction will be simply 1. So, that that F into 1, and there that other part of that in is what is that here as a makeup some amount of toluene whether it is coming or not. Since makeup is only for 100% hydrogen, there is no makeup amount of what is that toluene there. So, simply we can write that M into 0. Here M is that amount of that toluene amount of makeup is considered here, and also other quantity which is coming to the mixer is that amount of gas recycle there, that is Rg, but in that Rg what will be the amount of toluene? Since there is no toluene is coming out from the separator, we can say that in the gas recycle stream there will be no toluene. So, that is why it will be into 0 because Rg into then 0. And then other part is coming into the mixer is liquid recycle. Now, in that case as a liquid recycle amount is RL, but it this recycle stream will not contain other components except toluene. There 100% toluene is coming through this stream. So, there we can say that simply that amount of toluene will be equal to RL into 1.0 because 100% toluene is there. So, that is why we can write here 1.0. So, we can do this material balance for the toluene in this mixer like this. Now, this is your total in, but what should be the out? Out of course will be that outlet amount will be G. So, that is why this equation can be written as a material balance for the toluene. Similarly, we can do the material balance for the hydrogen. What is the amount of hydrogen is coming out into the mixer, that is as a feed it will be 0 because there is no hydrogen is coming into the mixer from this feed mixer. And then what is the makeup amount there? Of course, there 100% hydrogen will be supplied as a makeup there. So, we can write simply M there, and Rg there. Here in this case Rg, that is gas recycle, what will be the fraction of that hydrogen will be containing into that Rg? That simply you can calculate, because you know that what will be the mole of hydrogen and mole of methane in the mixer that is coming out from the separator here in this gas recycle stream. Now, that fraction will be equal to simply that moles of hydrogen divided by total moles of hydrogen and methane. So, accordingly hydrogen mole fraction you can simply calculate based on this amount as it is found by solution from this material balance of component in the system of reactor and separator. So, we can write here Rg into 327 by 327 plus 476. Why 327 plus 427? This is the total mole of hydrogen and methane, and since this 327 by total mole, this 327 is for hydrogen. So, we can write here hydrogen mole fraction. So, Rg into hydrogen mole fraction, that will be your total amount of hydrogen that is coming into the mixer. And then liquid recycle there RL, since there is no hydrogen there in the liquid recycle. So, we can simply write that the fraction will be equals to 0. So, RL into 0, simply that there will be no hydrogen gas in this liquid recycle. So, finally, we can write that hydrogen balance as F0 plus M1 to Rg into what is that this fraction plus RL, that will be equal to 400. Why 400 here? Because the amount of hydrogen that is coming out from this that mixer in the G stream as 400, because 1 mole of toluene will carry along with that 4 times of its amount. So, that is why that is 400. Similarly, methane balance if we do for this mixer, what we can get that what is the feed amount of that methane there. So, methane since there is no methane amount in the feed mixer, we can say that simply it will be 0, then you can write here F into 0. And similarly, in the makeup stream there will be no methane, so we can write here M into 0. But in the Rg, that is gas recycle stream, we can say that there will be a some fraction of methane in that gaseous stream that is coming out from the separator. So, in this case we can write similar fashion that earlier we have told that the fraction can be written as here what will be the amount of methane out of total moles of that methane and hydrogen. So, this is simply 476 divided by 327 plus 476 as per that is amount that we got from the material balance by considering that system of reactor and separator. And what will be the amount of methane that is coming out from the separator as a liquid recycle there, because in the liquid recycle there will be no methane. So, we can write that RL into 0, that means 0 amount of methane there in the liquid recycle. So, finally, this is your total in and what will be the out? Similarly, that it will be 400, because again as per problem that 1 mole of toluene will produce that 4 times of its methane according to the reaction. So, it will be simply 400. So, we can write here this material balance for this mixer system, and after substitution of this RL, if it is required, of course there it is required in this equation, and also that other moles of hydrogen and that methane amount there, and solving these 3 equations there, again we can get this F will be equal to 76 moles, Rg will be equal to 677.97, and M will be equal to 123.92 moles. So, in this case we can then have what will be the makeup amount, what will be the feed amount, and also that what will be the particularly that total amount of G that we can get there. Again we have to find out what should be the purge. Now, this purge basically that if we do the material balance over this system here in the divider, this is actually this divider we can write. So, in this divider if we say that this total amount of purge will be basically that what is the amount of mixture of methane and hydrogen is coming from the separator into this divider, and then what will be the amount of gas is recycled to the mixer here. So, if you subtract out the total amount of gas mixer gas recycle from this gas mixer, then you can easily calculate what will be the purge. Basically, you can do the material balance here in this divider. So, it will be simply overall material balance, it will come as here P that plus Rg, that will be basically that mixture of that total amount of hydrogen and methane, because here inlet will be equal to 2 outlet amount. So, in that way you can simply write that here P will be equal to n mole of hydrogen plus n mole of methane minus this Rg. This Rg already you have calculated based on that material balance, and then finally you can have this purge amount is 125.03 moles. So, this problem is that is a very good example of material balance, how to do the material balance with chemical reactions, with 1-pass reactions, and also that with multiple units. Also you can say that is there any bypass or not, if is there any that we can say that recycle or not, or is there any purge or not, or is there any makeup or not. So, based on all those components you can practice this problem, and you can have the idea how to do the material balance here. Next we will consider the material balance based on combustion reaction. Before going to that material balance based on the combustion reactions, you have to know that what is that combustion basically. So, combustion basically is a burning or oxidation of fuel to release energy, and fuel typically contains carbon, hydrogen and sulfur, even sometimes methane, propane, etc. Two types of actually reactions are in combustion reactions. One is complete combustion, where there will be no carbon monoxide, and also you can say that all carbon will be converted to carbon dioxide, all hydrogen will be converted to water, and all sulfur will be converted to sulfur dioxide. So, as per complete combustion, we will not have any carbon monoxide in the outlet streams as a product, and also we can say that there will be no there will be a complete conversion of carbon to the carbon dioxide, complete conversion of hydrogen to the water, and complete conversion of sulfur to the sulfur dioxide. Whereas another reactions, it is called that incomplete combustion reactions, where you will see that all carbons will go to the carbon dioxide as well as carbon monoxide, that is incomplete reactions. Okay. So, whenever you will get that carbon monoxide, that means you can assume that there will be an incomplete reaction. So, complete combustion of propane, here an example is given that this propane after oxidation it will give you that carbon dioxide and water. Similarly, incomplete combustion of propane, it will give you that carbon dioxide and water, but again this that propane will be reacting with oxygen and it will give you that carbon monoxide and water. So, basically it is an incomplete reaction. Now, for this oxidation reaction for the combustion, you will see that source of oxygen will be usually air, which will contain 21 mole percent of oxygen and 79 mole percent of nitrogen. And product gas that will be coming out after reaction, it will be called as stack gas, or you can say that flue gas. And you can consider that mixture as dry basis, where the composition excludes water, whereas that wet basis it will be there, where this composition of this flue gas or stack gas will be contains water there. So, a gas with 40% A, 40% B and 20% water will be called as wet basis combustion, flue gas, flue gas, and also if is there only 50% A and 50% B, there is no moisture is there, you can say that there will be a dry stack gas or dry flue gas. So, this is the basic concept of that complete combustion and incomplete combustion, and these are the reactions you will see that. So, based on which we will do some calculation as per material balance equation. Now, for this that oxygen will be supplied and there by that oxygen combustion will be there. Now, what will be the amount of that theoretical oxygen will be required for complete combustion, and accordingly what should be that actually air to be supplied, and if suppose certain amount of oxygen in excess to be required for the complete combustion in the feed stream, that also you have to calculate. So, for that you have to define that how to estimate or calculate that excess air or that excess oxygen there or no. So, in that case excess oxygen will be defined as amount of oxygen in excess of that required for complete combustion, and theoretical air which is required, that is quantity for air that contains theoretical oxygen there, and theoretical oxygen will be moles of oxygen that will be required by stoichiometry for complete combustion of all fuel. So, these three definition you have to remember. Now, accordingly we can say that the excess air will be defined as 100 into excess air by required air. This is percentage excess air. So, it will be 100 into excess oxygen by 0.21 and by required air, that means in terms of oxygen it will be oxygen by 0.21. Why that 0.1? Because air contains 21 mole percent of oxygen. This excess air also you can express in terms of that what will be the entering amount and also required amount of oxygen that you can express in that way. So, it is defined as 100 into oxygen entering the process minus oxygen required divided by oxygen required. Similarly, percentage excess air can be calculated based on that excess oxygen also, like 100 into excess oxygen divided by oxygen entering minus excess oxygen, like this. So, this definition you can use for your further calculation for your material balance. Let us have an example for coal combustion process, and for this coal combustion process how to do the material balance based on this combustion reaction. In this case let us say that the certain amount of coal that contains 72% carbon, 11% sulfur, and remaining, that is 17% hydrogen in mole, that will be burned in a furnace by an excess air. Assume all amount of coal is burnt as per following reactions. The compositions of the outlet streams are that shown in the figure here, and also in that case you have to consider that 100 mole per minute of dry gas flow in stream 3 as shown in figure in the slide. In this case we can say that coal contains carbon, sulfur and hydrogen, and if you burn this coal there will be a combustion reaction. Now the combustion reaction can be represented by this equation here, that is carbon will oxidized, it will give you carbon dioxide, sulfur will oxidized and it will be giving you sulfur dioxide, and hydrogen will convert it to the potato. So in this way of combustion reaction, if you consider that 100 mole per minute of dry gas that is flowing in the stream 3 as a dry gas, there based on which you have to calculate what should be the percentage excess air is required, and also what should be the ratio of water vapor and dry gas there in this particular process. As per solution, we can say that first of all you have to find out what should be the molar flow rate of nitrogen in the dry gas. Nitrogen in the dry gas, that will be that 78% that is in mole percent of nitrogen is in the that air stream. So it will be nitrogen amount will be 78 mole of nitrogen per minute. But here if we do not consider that the air stream, in this case very simple, that in the dry gas you will see that there it is given that only 78% of nitrogen they are in the stack gas. So here total amount of nitrogen will be here, since the flow rate of gas in the stream 3 is 100 mole per minute. So there will be a nitrogen will be equal to 78 mole of nitrogen per minute, it will be flowing there. Now this nitrogen gas is coming from actually air, which is supplied in the that furnace. So its amount is the same as that in the inlet air. So accordingly the inlet air molar flow rate will be is equal to what? Since it is the nitrogen amount, and since nitrogen contains in the nitrogen in the air is 70 that 9%. So we can say that here it will be that 78 mole of nitrogen per minute divided by 0.79. So it will be simply as 98.7 mole per minute. And then if you do the carbon atomic balance for this system, that carbon atoms in the feed that will be equal to carbon atoms in the product. So this is your in is equal to out for that carbon atoms. Now this carbon atoms in the feed, what is that amount? It is that of course will be equals to what is that here 100 moles into 0.09 plus 0.03. Why? Because in the outlet streams that carbon is coming as carbon dioxide and carbon monoxide. This carbon dioxide and carbon monoxide is basically coming from the source of that coal in the that feed stream. So what will be that carbon dioxide in their stream, and what will be the carbon atoms there, that will be basically 100 into 0.09. And similarly other the carbon is coming from that that coal stream as a carbon monoxide here in the dry gas, and its fraction since it is 0.03, out of that 100 moles of rate. So we can simply say that total amount of carbon will be equal to that 100 into 0.09 plus 0.03. So, it will be amount of 12 mole of carbon per minute. Now, this carbon, of course, it will come from that feed stream. So, what should be that then feed stream flow rate that you have to calculate. Say that this feed stream flow rate is an N1. So, we can simply write that this carbon balance for that. So, we can write N1 into 0.72, that will be actually equals to that carbon in the dry gas. So, it will be simply 12.0 mole, which implies that N1 will be equal to what, this here like this. So, this is it is per minute. So, we can write here per minute. So, here it will be per minute. So, here we can have here as per material balance that what would be the feed stream flow rate in the stream 1, that will be equal to N1 and it will be equal to 16.7 mole. And after that if you do the atomic sulfur balance, then you can say that the moles of atomic sulfur in the feed will be equal to 1.8 mole per minute, and moles of atomic hydrogen in the feed will be equal to 2.8 mole per minute, and accordingly the number of moles of oxygen that will be required for complete combustion of carbon, sulfur and hydrogen, that basically as per this equation, because here 12 mole of carbon that will require how many moles of oxygen. Simply here it will be 12 mole of oxygen, because 1 mole carbon requires 1 mole of oxygen. So, that is why basically 12 mole of carbon will actually require 12 mole of oxygen. Similarly, since here 1.8 mole of sulfur is in the feed stream, so we can say that for this 1.8 mole of sulfur will require similarly here 1.8 mole of oxygen, because 1 mole of sulfur will require 1 mole of oxygen. Similarly, 2.8 mole of hydrogen in the feed stream. So, this 2.8 mole of hydrogen will require 0.7 mole of oxygen. Here in this case, as per reactions, you will see that here 2 mole of hydrogen will require 0.5 mole of oxygen as per reaction. So, accordingly we can say that 2.8 mole of hydrogen will require that 0.7 mole of oxygen. So, total theoretical oxygen will be required for the complete combustion will be equals to this 12 plus 1.8 plus 0.7. So, it will be total 14.5 mole per minute. This is your theoretical oxygen, but total inlet oxygen in the feed air, what will be that? You know that total inlet oxygen in the feed air, that will be equal to that calculated based on that what will be the nitrogen amount there in the feed stream, and accordingly it will come, because in the air you will see that 79% mole of nitrogen will be having, along with that what is the 21% of oxygen. So, if there is 78 mole of nitrogen there in the air stream, so we can say that how many moles of oxygen will be in the feed stream. So, it will be simply by 20.73 mole of oxygen in feed by minute. So, this is where you can calculate what will be the total that inlet of oxygen in the feed air. So, once you know this that supplied oxygen in the feed air is 20.73, whereas theoretical oxygen required for the complete combustion in the burner or furnace, that will be equal to 14.5 mole per minute, and based on that that you can calculate what should be the percent oxygen there, and then what should be the percent excess air also there. Now, if you calculate that percent air, then you have to consider that what would be the amount of excess air is required there. Now, total inlet air is that since that only nitrogen amount, so 0.79 mole of nitrogen is having in 1 mole of air. So, 78 mole of nitrogen will be having in how many moles of air? It will be simply here as per calculation 98.7 mole per minute. So, excess air, that is equal to excess oxygen. Okay. So, according to that, total theoretical air will be equal to, that is 14.5 is the theoretical oxygen is required. So, you have to convert it to what will be the amount of theoretical air to be required just by simply dividing this 14.5 by this 0.21 of oxygen fraction. So, it will be simply 69 mole per minute. So, percent excess air will be equal to here excess if we as per definition, that is what will be the supplied amount and what will be the theoretical amount of air. So, supplied is 98.7 and theoretical is 69. So, divided by theoretical air required. So, accordingly it will be coming as 43% of excess air required for this complete combustion. Now, if you assume that all water in the product gas is from the combustion process, now from that 2.8 mole of hydrogen that is reacted, 1.4 mole of hydrogen will be produced based on that reaction. Then ratio of water vapor to the dry gas will be simply 1.4 divided by 100 mole of dry gas. So, it will be simply 0.014 mole of hydrogen per mole of dry gas. So, in this way we can that do the material balance for the combustion reaction. Another example, we can say that if a fuel oil containing 87 weight percent carbon, 10% hydrogen and 3% sulfur, that is fed in a furnace and burned with 25% excess air. Now, analysis of the furnace exhaust gas results only nitrogen, oxygen, carbon dioxide, sulfur dioxide and water. The sulfur dioxide emission is actually controlled by some absorption process in an absorber. So, in that case the gases like nitrogen, oxygen, carbon dioxide and some of that water and sulfur dioxide that is entering to the unit, that will leave the absorber and pass out to a stack, and as the absorber is of limited capacity, you will see that a fraction of that furnace exhaust gas will be bypassed directly to the stack there, and you will see that the absorber removes 90% of the sulfur dioxide in the gas feed to it, and combined stack gas contains 612.5 ppm, it is called parts per million, that sulfur dioxide on a dry basis. Now, this means that every million moles of dry stack gas contains 612.5 moles of sulfur dioxide. In this case, you have to calculate what should be the fraction of the exhaust bypassing the absorber at this condition. Now, see here the flow chart of the problem is given here. This is one furnace, and in the furnace 100 gram of oil is coming with its composition here like carbon, hydrogen, sulfur and oxygen, and n mole of oxygen is supplied here in the furnace, whereas 3.76 into n1 mole of nitrogen as 25% excess will be supplied to the furnace for the combustion. And after combustion, you will see that there will be a exhaust gas from that furnace. It will be containing N2 amount of nitrogen, N3 amount of oxygen, N4 amount of carbon dioxide, N5 amount of that sulfur dioxide and N6 amount of water. Now, from this mixture, some amount of this mixture will be bypassed here like this as shown here. This is bypass there, this is bypass that absorber unit, and some fractions will be allowed to pass through the absorber to absorb some that gases, and then outlet gas from that absorber again will be mixing with that bypass amount, and it will go to the stack, and some amount of that gaseous product as a sulfur dioxide, it will be taken out from that absorber after absorption as this amount as shown in here in the figure in the flow chart. Now, accordingly you have to calculate what should be the fraction of the exhaust bypassing that absorber at this condition. Now, let us solve this problem here. So, this is your flow chart given in details. Now, if you consider that carbon dioxide first to do that material balance. Now, you will see that this carbon dioxide, that is in the feed stream, it is 87%. So, if it is 100 moles of total feed, then it will be that carbon will be 0.87 into 100 this gram of carbon. And since the molecular weight of carbon is 12.01, so amount of carbon in terms of mole, it will be this divided by 12, and again 1 mole of carbon converting to carbon dioxide, that will be 1 mole. So, basically you can say that this N4, whatever it is coming out from that furnace as a carbon dioxide, this amount will be exactly the same of this 87% of carbon in the feed stream. So, accordingly we can say that this N4 will be equal to 7.244 after calculation, and for this 7.244 mole of carbon dioxide will require how many moles of oxygen for its combustion or this complete reaction. So, it will require 7.244 mole of oxygen. Similarly, for water, if you consider that, what will be the amount of water that is supplied in that furnace as a feed stream, that will be 10% of that as hydrogen, and that hydrogen if you convert it gram to mole, and then 2 moles of hydrogen will give you that 1 mole of water. That means here this amount of water is actually being supplied there, but in N6 you will that this moisture will come from that furnace as N6 mole. So, N6 will be equal to like this. Now, this for this N6 of course you know that how much oxygen will be consumed there, it will be that according to that reaction it will come out 2.475 mole of oxygen. Similarly, you can do the same way for sulfur dioxide, and in that case this N5 as a sulfur dioxide, it will be 0.0936 mole of sulfur dioxide, which will require 0.0956 mole of oxygen for its consumption for the reaction. Now, since there is 25% excess is there of that oxygen, we can say that this N1 will be equal to, as per this here this N1 what is that N1 here, this N1 is here basically that mole of oxygen that is supplied to the furnace. So, that N1 can be calculated. This is required oxygen, and since it is the 25% of excess, so it will be simply you have to multiply by 1.25 with this that what is the oxygen consumed for that complete combustion. So, it will be coming as 12.27 mole of oxygen. Similarly, if you do the oxygen balance for N3, then you can say that this N3 will be equal to what? Basically, this N3 will be equal to here what will be the mole of oxygen is coming out from the furnace, that will be coming out from the feed stream after reaction consumption, and then we can write that this amount will be equal to here 12.27, that is actually that excess amount of feed of oxygen, whereas required amount is 7.244 plus 2.475 and 0.0936 as per that oxygen consumption based on that that reaction. So, accordingly you can say that this oxygen balance, that is N3, which is coming out as unreacted oxygen, this will be equal to 2.46 mole of oxygen. Similarly, you can do that nitrogen balance here and also sulfur dioxide in stack, sulfur dioxide balance around that mixing point. In the mixing point, if you consider that here in this case at this location before stack. So, we can have this that sulfur dioxide in the stack like this. Similarly, total dry gas in stack, assume there will be no carbon dioxide, oxygen or nitrogen in the absorbed in the scrubber, or scrubber means absorber, we can say right here absorber. So, we can say that this the total dry gas balance, if you do that in this way, you can simply calculate what should be the amount of fraction of X there for the sulfur dioxide, there you can easily calculate them. And since 612.5 ppm of sulfur dioxide dry basis in the stack gas, so we can say that this fraction of bypass will be equal to that 0.295 as per that dry basis. So, this is that one example by which you can say that how to do the material balance for the combustion reaction, and also you can do the material balance for this combustion reaction with excess oxygen, with excess air, and how to calculate that theoretical oxygen, theoretical air, and based on which how to calculate that excess oxygen is required for that combustion reaction, or also what will be the excess amount of air to be required for that complete processes. So, I think this will be helpful to understand the know-how of the material balance for this combustion processes, and also I think you will get the idea to do the material balance further with some other problem. So, I would suggest to follow this textbook given in this slides for further understanding of the material balance with this combustion process.